Hey guys, this is the last set of notes for Unit 3. In Notes D, we're going to talk about intermolecular forces. But first I should tell you, the bonds that we've been talking about are actually called intramolecular forces. So just to recap the intramolecular forces real quick, the strongest one was called the ionic bond. The next one would be a polar covalent bond, and then the non-polar covalent bond. So remember that polarity had to do with the difference in electronegativity, and then the ionic bond had to do with the total difference of having a +1 charge and a -1 charge, whereas these were just partial charges, and here we have no charges. So the attraction all has to do with how great the opposite is, because opposites attract, right? One thing we haven't talked much about is metallic bonding. So just to give you an idea of what metallic bonding is, not that I want to spend a lot of time on it, in a sheet of metal, let's say iron, you would have some iron nuclei floating around, which would be positively charged, and the electrons would be floating around in what we call the electron sea model. See how that kind of looks like a sea of electrons? So the idea is the electrons are completely delocalized, that they're able to just flow back and forth throughout the sheet, which is why metals are such good conductors. So that is still considered an intramolecular bond. It's just the weakest of all of them. So these 4 types of bonds are what hold atoms together inside of a molecule. Intramolecular bond. What I want to talk about next is something called an intermolecular bond. And that's going to be an exterior bond between molecules. So intermolecular bonds are between 2 different molecules. Say I had 2 separate water molecules. The bonding between the hydrogen and the oxygen would be intramolecular, but the bonding between the 2 water molecules would be intermolecular. And this is what drove the phase changes. If you remember, there was a plateau during a phase change, if you're looking at the energy. Well, that's because the energy is going into breaking the intermolecular attractions to allow those molecules to be further apart. So let's look at the intermolecular attractions and phases. It's actually going to be the strongest in the solids, and that's because the solids are closest together. So the molecules would feel each other's intermolecular attractions much more strongly if they are closer together. Then those weaken a little bit through melting, and so the molecules can get a little further apart, which is why they're able to kind of move over each other. Think like viscosity, like how they're able to move, how fluids are able to run. And then we're going to break, theoretically, all of the intermolecular attractions in order to make an ideal gas. So the gases would have the most chaos, the most heat energy, and therefore the most kinetic energy, be moving the fastest. Remember, that's according to kinetic molecular theory. So with the gases, we're going to have the weakest intermolecular forces because the particles are so far apart and moving so fast that they don't feel each other. So they're not going to feel these attractions. So in order to order the forces, they would be strongest in the solid, next liquid, weakest in a gas. The attractions between particles. All right, so there are 4, well, they're kind of 4 main types. Really, we have ion-ion interactions or interactions between 2 ionic compounds. And then we have something called a dipole-dipole interaction, but there happens to be a certain version of a dipole-dipole interaction which is stronger, and we call that a hydrogen bond. This is actually going to be the focus of the lab that we're doing. So you want to make sure you pay attention to the hydrogen bonding part of these notes, but also know that they fit as a subcategory for dipole-dipole. Since this is in order of strength, though, you see the hydrogen bonding on top of the dipole-dipole. And then the last thing that we're going to talk about is called a London dispersion force, or LDF forces. All right, so let's start with ion-ion interactions. So this would be an attraction between 2 ionic compounds. So this is a few examples. Where are we? Here we go. So sodium and fluorine coming together. Notice you have metal and nonmetal. So that would be an ionic bond. Metal, nonmetal, metal, nonmetal. So we have all ionic compounds here. In order to determine which of these substances would have the strongest bonds, I want to look at the differences in their charges. Remember that opposites attract. So the more opposite the charges, the stronger the bond. So what was the charge on the sodium? Think periodic table. It's in the first group. It's going to have a +1 charge. Fluorine, being a halogen, has a -1 charge. So the opposites, the difference between +1 and -1, would be a difference of 2. Think about the number line. Going from +1 to 0 to -1, you have a difference of 2. Now let's think about the calcium and the oxygen. Calcium is in the second column, so it would have a charge of +2. And then oxygen, being in column 16, would have a charge of -2. So what's the difference as you go from +2 all the way to 0 and then out to -2? What's the absolute difference? That would be a difference of 4. Now let's look at the CaF2. Calcium, as we just said, is in the second column, and so it would have a charge of +2. And fluorine, being a halogen, would have a charge of -1. It doesn't matter that there's 2 of them. I'm interested in the difference in a single bond. So the difference between calcium and a single fluorine from +2 to -1 would be 3. This is one of the few times where having a subscript does not matter. So don't let that throw you off. Now, if the bigger difference means a stronger bond, that's going to affect our melting point. Because in a melting process, we're breaking those intermolecular attractions. So if they're stronger, they're going to be harder to break. So what would be hardest to break? The NAF, CaO, or CaF2? The greater the absolute difference, the stronger the bond. So the greatest absolute difference is 4. And so the highest melting point then would be CaO. What would have the weakest bond? That would be the thing with the smallest absolute difference. NAF. And of course in the middle, we would have our absolute difference of 3, CaF2. So that's how we order our melting bonds, our melting points, from the weakest, smallest difference up to the strongest bond having the greatest difference. So our intermolecular forces all have to do with the difference in charge. The greater the difference, the stronger the bond. All right, in a moment, on to what is a dipole-dipole interaction. So notice I went from 5 to 7. Remember, 6 was a version of 7. The hydrogen bonding is a version of the dipole-dipole interaction. So the dipole-dipole interaction is going to be an interaction between 2 dipoles, just like an ion-ion interaction was a difference between 2 ions. So to have a dipole, I would need a polar molecule. HCl is a great example. Chlorine is more electronegative than hydrogen, and so I would have a partially negative charge on the chlorine. Same idea with the other molecule of the HCl, but the hydrogen is going to be partially positive. So the attraction between the partially negative side and the partially negative side and partially positive side, that positive and negative is going to attract. It'll be weaker than an ion-ion because it's partial, but it's still opposite, so it's still going to attract. So that's going to allow these 2 molecules to kind of like each other, support each other. That's our dipole-dipole interaction. Now, what could make this version of an attraction even stronger? It's all about the opposites attract, right? The negative attracting the positive. So if this were more electronegative and this was less electronegative, that would increase the attraction between the 2. So if I had this set to one of our most electronegative atoms, like fluorine, nitrogen, or oxygen, then that would indicate that I would have a very negative side of the molecule. And that could be attracted to a positive side of another molecule. And because they're more opposite than something that's less drastically different in electronegativity, that's going to be a really strong bond. So that's what hydrogen bonding is all about. In order to have a hydrogen bond, you have to have a hydrogen, which is the nonmetal with the lowest electronegativity. And then we have to have nitrogen, oxygen, or fluorine, which are the nonmetals with the highest electronegativity. So it's going to be in between ions having full charges and any old polar molecule having just some partial charge. It's going to be a super strong partial charge. So that would fit in to number 6 in terms of strength. So here's our hydrogen bond between the oxygen, one of our 3 especially electronegative atoms, being attracted to the hydrogen, which is partially positive. So water is the ideal molecule that we can talk about exhibiting hydrogen bonding. So there are 3 main properties that we get when we have this specially strong dipole-dipole interaction known as hydrogen bonding. The first is called surface tension. So you may have seen a little bug floating on water, how the bug can just float on water. You can actually even float a paperclip on water. Even though the paperclip is metal and should be more dense and sink, the surface tension can hold it up. So surface tension acts kind of like a net on the top of the water, and you can float things that would otherwise sink because the surface tension holds it up, because the attractions between the 2 water molecules are stronger than normal. 2 other properties that are related to each other. We have cohesion and adhesion. So cohesion would be between 2 water molecules, forces that attract. So have you ever taken a cup and you fill it up with water and you're able to actually fill it a little over the brim without gravity pulling it to the side? That would be an example of the cohesive forces at work. The individual water molecules are attracted to each other, and so they're kind of overwhelming the force of gravity for the moment. They're holding each other together so that they're not pulled down. Of course, it only works for a little while. If you make it too high, it will overflow. There are also adhesive forces. So adhesive forces are going to be between, say, the water molecule and something else. Have you ever had your blood taken in a way that they like prick your finger, and then they have this little glass tube and it doesn't have any kind of suction, anything on it, little glass tube, and they just touch it to the blood and the blood just climbs right up the tube? That's because the blood is made of a lot of water, and so that water is attracted to the glass and it will just climb up to try to get to the glass. Be an example of adhesion. So some substances have stronger cohesive forces. For example, mercury would have an inverted meniscus, where the mercury particles are more strongly attracted to each other than they are to the glass. Water actually has stronger adhesive forces. Although it does have both, it would rather climb up the glass than pile up on itself. So sometimes the cohesive forces win, sometimes the adhesive forces win, but most molecules do have both. All right, and our last intermolecular force is called a London dispersion force. So London dispersion forces, typically called LDF forces, are super temporary. They're number 8 in strength, but if we numbered these, I could do, like 1, 2, 3, 4. Our intermolecular forces are quite a bit weaker. And then in order to put London dispersion forces to scale, I would need to drill like 6 feet into the ground. It is so much weaker than any of our other forces. It is super temporary. So what creates a London dispersion force is actually simply the electrons rotating. So even something like a noble gas, which doesn't even have a bond, is able to experience London dispersion forces because all atoms have electrons that move. As the electrons move, they will naturally clutter in one area of the atom at one small temporary instant. During that very small temporary instant, that part of the atom would be more negative than the other part of the atom. If this happens in 2 separate atoms, you would have a partially positive part of one atom and a partially negative part of another atom. And those very partially, very temporarily charged parts would attract. How strong does that sound to you? Super duper weak. But it does play a role. It can allow the atoms to be attracted to each other. It's just constantly always changing. They call them induced dipoles, where if I put something positive close to another atom, it might attract some of the electrons. And so we can get them in sync and get some interesting properties, but generally speaking, this is just a super temporary weak force. The thing I used to always forget, just to kind of give you a heads up, every single atom, every single molecule has London dispersion forces. So if I'm asking you to list what force a molecule or atom has, always include London dispersion forces because everything has moving electrons. All right, so that wraps up The different types of forces. Let's put together a little chart to kind of summarize. For the intramolecular bonds, we had 1, the strongest bond, being ionic. 2 would be polar covalent. And 3 would be non-polar covalent. And then we also mentioned that metallic bonding, just so you also know that it's intramolecular. Just to make a parallel here, the intermolecular bonds, the strongest one was between 2 ions. So see, ionic bond being the strongest intramolecular, and then the strongest intermolecular would be between 2 ions. Then we're going to look at polar covalent bonds. So we had dipole-dipole interactions on the list. If I could spell dipole, there we go. And so that would be a version of our polar molecules, also known as dipole, being pretty strong attraction. But there was a version, remember, a subcategory of dipole-dipole that was even stronger, which is where number 6 came in, our hydrogen bonds. All right, and then if it's nonpolar, metallic bonds, even just regular old atoms, everything can have number 8, put a little distance here, our very weak attraction known as London dispersion forces, where the electrons are simply rotating, and so they would have a little bit of a negative charge in one spot, a little bit of a positive charge in another spot. So you can kind of see the trend overall is that the greater the difference in charge, the more the opposites will attract. That's kind of the main idea here. So that's going to wrap up all our notes on intermolecular forces and everything from Unit 3. So the next set of notes will be on Unit 4, where we're going to get into the naming of these different molecules.